Hi, dear audience. Thank you for attending the afternoon session for the Computer Vision in the Wild workshop. So I'm Haotian Zhang from the University of Washington. Hope you have enjoyed the morning session so far, and I believe that you will also get a lot of insights during the afternoon sessions. So basically, there will be two sessions in the afternoon. So I will be chairing the first session, and Ashiwaya from New York University, that she will be responsible for the second session. So for the first session, the schedule is that we will have our first speaker, the Ishan Misra from Meta. So he will talk about the general purpose visual recognition systems. And then Yongqing Xian from Google, he will present his work on the zero-shot image classification via learning and supervised semantic embeddings. And afterwards, followed by Yongqing's talk, so we will also have 8 spotlight papers to be presented. So now I will handle this to Ishan. So before Ishan's talk, I think I will briefly introduce him a bit. So Ishan Misra is a research scientist at Facebook AI Research Fair, where he works on the computer vision and machine learning. So his research interest is in reducing the need for supervision in visual learning. So for his work in self-supervised learning, he was featured in the MIT Tech Review's 35 Innovators Under 35 list. So today he is going to give us an exciting talk about general purpose visual recognition systems beyond a single modality and a task. So now let's welcome Ishan.
Thank you for having me today.
Thank you.
Start sharing my screen. Right. Not letting me present back.
Oh, probably you can click the play, maybe. I'm not sure.
Yeah, I'm not able. Oh, okay, now I see it. Okay, it was hidden for whatever reason. All right.
Okay.
Cool. Right. So thanks for having me. Today I'll be talking about general purpose visual recognition systems. And my goal is to convince you that we need to really start building such recognition systems which work beyond a single modality and a single task. So the current state of computer vision is pretty good. We have a bunch of these visual recognition models that are good for specific tasks. So if you think about a particular task of object detection or segmentation, today we can build very good models that can recognize a number of categories and are very good at segmenting out pixels belonging to that particular category in a very precise manner. If you think about tasks on short video understanding, we can design against specific models for that specific problem and solve them pretty well. And the same goes for a bunch of these image text tasks where you have images and paired text data, and now you can solve a bunch of image classification tasks, also like in a zero-shot manner. But again, this is very specific to image classification. The big sort of problem with this is that our visual recognition systems are actually not generalists at all. So for each of these domains and each of these problems that I described earlier, we need to train specific models for that task and that particular modality. This is in very, very stark contrast, right? So ML models essentially are very picky eaters. So if you give them a new modality or a new different task, then they're not really going to work very well. So in the past, we've designed a bunch of these recognition architectures specifically for domains. So if you have images, we design basically 2D coordinates for them. If you have videos, we try to extend these 2D coordinates and try to make them work on the temporal axis. If we have single view 3D or 3D in general, then we design specific architectures designed for that particular modality. Now, what this ends up doing is if we have supervision or if we have particular task labels for a modality, then they don't transfer very well to the other modality. For example, if I had a lot of labeled images of pineapples, I will not be able to recognize pineapples in 3D because I was training a completely different network from scratch on 3D data. So it's not really going to work very well for 3D recognition. And so really what we need is supervision that is particular to that modality for that particular task. And so it really narrows down the scope of things that we can do in real life. And when we talk about task-specific architectures, even if the task is very shared, for example, pixel labeling, where you are trying to assign labels to pixels, depending on the type of label, we still have specific architectures. So if you're trying to solve semantic segmentation, where you're trying to assign labels to each pixel, but you don't really care about different instances, we use fully convolutional networks or UNets. If we move to instances, where you are trying to predict pixels for each instance and distinguish between instances, we use box-based architectures or object-sensitive architectures like Detector. For panoptic segmentation, where we're trying to do both, we actually use a different architecture completely. And it makes no sense, right? Because all three of these tasks are solving the same or a very related problem of trying to label pixels. So this makes it also very tricky because we need now exactly the right kind of supervision for that kind of task. So detection model, for example, cannot use a lot of supervision from another type of task. So if we had a lot of image label data, we cannot really use it directly for detection. And the only successful way of using this type of supervision is pre-training. So we take a large model pre-trained on a bunch of images and text, or images and say class labels, and then we transfer it by transfer learning to do detection. But essentially, if we knew how to classify a lot of images and a lot of categories, that knowledge does not transfer into detection because we really need that exact supervision to solve the detection problem. So, and like I said earlier, we cannot really leverage supervision across different modalities. And this is, again, a big, big challenge. So in general, this talk will really focus on building general purpose vision models. And I'll split it up into two parts, which is going to be general architectures, which are architectures that work very well across different modalities or different tasks, and general models that basically will learn from different types of supervision. So in particular, I'll talk about these three works: Omnivore, which is a single model that works for images, videos, and 3D; Mass-to-Former, which is a single architecture that works very well for all types of pixel labeling tasks on images and videos. So you can do panoptic, instance, or semantic segmentation; and Detic, which will actually be presented at this year's ECCV, which is a detection model that can learn detectors using image labels. And so now you can have a detector that can classify 20,000 or even more number of classes. All right, so let's first start with Omnivore. So this was joint work done with these co-authors and was presented at this year's CVPR. So the goal of this paper was to design a single model that will ingest together multiple different modalities. So if you're given images, videos, or single view 3D, you want to feed them all into a single model. Now, this omnivorous model, our hope is that once we try to train a single model doing this, it can automatically enable cross-modal generalization, because we are learning a single representation for both, say, RGB and RGBD. If we were to encode both of these views, like both of these different types of pineapples, an image of a pineapple or a single view 3D model of a pineapple into a same representation, then now if we can recognize or classify the image of a pineapple, we should automatically be able to classify the RGBD image of a pineapple as well without any supervision. The second advantage is that it really saves a lot of engineering effort. So if you look at the progress made in images and videos, they happen in parallel, right? So you design handcrafted features like Swift or Surf for images, and then there are counterparts to that that are designed for particularly videos. The same thing goes for ConvNets, where basically we design a bunch of these architectures for images, and then we design their 3D counterparts. The same thing has actually happened with transformers as well. But at every stage, we're kind of duplicating effort because we're designing something and then we're slightly modifying it. Why not just like train something jointly on both of these modalities together? And finally, if we get a different modality at test time, or if we have varying number of modalities, we can deploy the same model across a bunch of different devices. And so it's the same model that will serve basically RGB classification, also do RGBD classification, and it really saves a lot of engineering effort again. So the training pipeline for our Omnivore model is pretty simple. If you have three types of modalities, in this case, image, video, and 3D, you first sample a modality and a mini batch from that modality. So for the illustration purposes, I'll basically sample a mini batch from video. Once we sample this mini batch from video, we tokenize and project it to convert it into a bunch of embeddings. And then we process it using a single transformer. And then we have a modality specific head. So in this case, we have a video head that's going to classify this video into a bunch of different action classes. And then we'll train this model and update it with backpropagation. So if you look at this architecture, the only thing that's different across modalities is the tokenization head, tokenization layer, as well as the classification head. But the bulk of the parameters that are in the transformer are completely shared across the three modalities. And so what you'll end up getting is a shared embedding space that contains all of these three modalities. Now, the other thing that we do is we show that you can train such a transformer without using any paired data. What that means is we actually use off-the-shelf datasets like ImageNet, Kinetics, and Sun RGPD, where you have almost no semantic overlap. And so in this case, these three datasets are constructed independent of one another, and you don't have the setting where a single sample is actually observed in images, videos, and 3D. And so we can basically train using these off-the-shelf datasets. You don't need to go and collect new datasets for training omnivorous models. One key property that emerges from training these models is that despite the fact that they're trained without any shared or paired data, they can actually learn how to share representations and enable cross-modal generalization automatically. So in this case, we look at an image, we compute its representation using an omnivorous model, we'll get some features, and then I'll try to look at nearest neighbors in different modalities, for example, in depth or in 3D and so on. And so if you look at the depth maps that we retrieve in this case, they end up looking exactly, they're basically the same class. So they're actually depth maps of pineapples. If you look at single view 3D, it's actually single view 3D maps again of pineapples. And finally, if we look at videos, they are also videos of pineapples again. And this property, like we can repeat this for a bunch of instances, like Halloween pumpkins for golf carts, and you actually end up seeing that it's learning to share this representation across these three different modalities. What the other thing we found is if you scale the model architecture, omnivorous models actually start doing really well and outperform specific models trained for specific tasks and specific data sets. And in general, Omnivore is state of the art basically on image classification, video classification, and single view 3D classification compared to architectures designed specifically for that particular modality or that particular task. And it sets a new state of the art on a bunch of different tasks, specifically on NYU segmentation as well. All right. Finally, my initial motivation, we can actually train a model to recognize a pineapple in images, and Omnivore basically, in a zero-shot manner, can recognize a pineapple in 3D. And we also showed very recently that Omnivore can actually be trained in a completely self-supervised manner. And we used the MAE model to train this, so the MAE training paradigm. And we take an Omnivore model, train it in a self-supervised manner on ImageNet and something, which is a video dataset and an image dataset. And we get a single model that is now state-of-the-art on both image classification tasks and video classification tasks. All right, so that brings me to the second part of my talk, which is going to be about Detic. And Detic will be presented as a poster on October 27th, so feel free to stop by the poster as well. So this particular work aims at training a detection model, which has a very, very large vocabulary. And what we end up showing is that you can train a detector which has a vocabulary of more than 20,000 categories without having explicit detection supervision for those classes. Now, the key insight here is that object detection can really be split into two very separate problems. The first one being localization, and the second one being naming. So localization is all about figuring out what objects are in the image and just sort of drawing a box around them. And at this point, we don't really care about the nuances between different types of objects. Is it a particular breed of dog or is it a cat? We don't really care about doing that. All we are saying is these are the different types of objects that are present. And in the second stage, which is naming or classification, we really try to name things given a particular taxonomy or given a particular ontology. And in this case, we're just describing them with course level object classes, so fish or bear and so on. Now, in a traditional detection setup, when we're training detectors like Mascar CNN or Deter, we actually couple both of these problems very tightly. And what that means is we need both of these types of supervisions on the dataset to train the model. So we need both the box location and the semantic category associated with that box when we're training such a model. Now, if you were to look at the number of classes that are available in these detection datasets, it's actually really, really small. So Coco has 80 classes, and even the most recent dataset like Elvis really has about 1,200 classes. And compare this to something like ImageNet, which has basically 22,000 classes, even though it was collected almost 10 years ago now. Now, this basically gives us the idea that if we can decouple this notion of classification with detection, we can probably leverage large-scale image datasets and expand the vocabulary of object detection models. The other problem that we observe in object detection datasets is that they have a very long tail. And this tail actually drops very quickly and does not cover a lot of classes. So here I'm showing you the number of images versus number of classes for 3 different datasets: Elvis, ImageNet, and conceptual captions. And for Elvis, we see that we have, again, only 1,200 classes, and there's a very, very sharp decrease in the number of images per class beyond this mark of about 200, 300 classes. You see a similar drop for datasets like ImageNet or conceptual captions, but just because of the fact that there are so many images in these datasets, you still get a significant number of images for a lot of these tail classes. So here's one example. We try to take a state-of-the-art model trained on Elvis, and we try to recognize this fairly common class lion. And what we find is that the detector trained on Elvis is really bad at recognizing lions. And these are actually pretty simple images, right? You have a lion which is pretty big. It's not an atypical lion. And you have it fairly nice, centered in the image. There's no self-occlusion. There's no occlusion either. And the detector is really bad at recognizing this lion. It says it's a dog or a cow or a bear. Although in all of these cases, you can notice that it's actually getting the bounding box correctly. It seems to be a naming problem. And this is not that surprising. If you look at the number of images of lion in Elvis, you get only 43 images. And so the detector really knows how to detect the object, but has a very hard time naming the particular object. Now, if you think about ImageNet, and you look at the number of images for this class lion, you get a lot more images. So really, and on ImageNet, this is not a really rare class anymore, and this is not a rare class problem. So our key idea over in this paper, Detic, was to learn localization from detection labels and learn classification or naming from image level labels. So we're able to decouple both of these problems. And now if you merge them together, finally, you'll be able to get a detector which is able to name and detect things and lots of categories. So the training setting for this model is that we take a detection data set with limited vocabulary. So in this case, it's Elvis. So you have about 1,000 classes. And you have a classification data with a much larger vocabulary. So in this case, we consider all of ImageNet. So that's about 20,000, 22,000 classes. And now we're going to train a detector using both of these labels. Now at test time, our hope is that this detector can now detect all of these 20,000 classes from ImageNet. And essentially it can name lots of things that even though it has never seen detection level labels for them. And the second thing we show is that if you leverage recent advances in zero-shot learning, for example, the OpenAI CLIP model, you can actually convert Detic into a zero-shot detection model, and you can just type in the object category that you want, so rock or like a blue snake, and it can go and detect this particular object as well. All right, so it's very straightforward to train a detector using detection data. I mean, this is basically what has been developed by a lot of people earlier. But how do we really train a detector using classification data? This is also a pretty well-studied field, but what we found is that actually we can make things a lot simpler. We propose a very simple way of training detectors using this image level data, where we consider the entire image as a bounding box. And so when you get this image of a lion, we just add a fake ROI into your mask RCNN model, where we consider the entire image as a bounding box, and we just compute a loss based on this. So whenever we get detection data, we train both the localization branch and the classification branch of the detector. Whenever we get the classification data, we inject a fake bounding box and train only the classification layer of the model and do not train the localization layer. So the RPN, for example, will not get a loss on the classification data. The key idea here is that if you try to pseudo label the data, if you try to assign which one of the RPN boxes contains a lion, you may miss out on certain instances. If you have 2 instances in this case, you may not assign it to the right instance. And that's actually where a lot of prior work tries to innovate on this pseudo labeling problem, which we find does not work very well when you scale to large data sets. The second idea is to replace the classifiers that we have, which are learned basically in, say, mask-CNN, by word embeddings. So in this particular case, we'll use the clip models embeddings to basically train classifiers. What this enables us to do is that when you have a novel class, which you just write a description for, you can compute a word embedding for that novel class, and then just use the embedding that you get for that class as a classifier, and then essentially learn how to name multiple objects. All right. So once we take our Detic training paradigm, we can apply it to basically a bunch of different detectors. So in this case, we apply it to mask-CNN, CenterNet2, and deformable deter. And we're measuring the performance on the Elvis dataset. And we're splitting it up into the MAP, which is the aggregate MAP for the entire dataset, and the MAP for the rare classes. And what we observe is that the rare class MAP goes up by a significant amount for each of these different detection architectures. And it turns out basically that when you look at these rare classes in Elvis, they're not so rare anymore if you're looking at all of ImageNet, and you can transfer that knowledge, transfer that naming capability that you get from ImageNet onto Elvis. The other thing we could do in this work is actually evaluate this entire detector in a completely zero-shot manner on a bunch of different data sets. So in this case, we looked at objects 365 and open images, and our model does really well without actually fine-tuning on any of these data sets. Seems to work very well across these different tasks, which means that you can learn not only very well detectors for like rare classes, but also good zero-shot detection capabilities that work across different benchmarks. There's an online demo built by folks at Replicate, which you can play around with. And when we posted our paper, there was a lot of fun results posted by users on Twitter. And so here's Detic being applied to images. It has actually never seen these kind of images. These are actually either cartoons or paintings. And we trained our model on Elvis and ImageNet, which is primarily natural images. So it's actually good to see that this model generalizes pretty well. It's able to recognize lots of small objects, predict masks for them, and predict bounding boxes. And it works pretty well also on the cartoon images shown on the right. This final part of my talk is going to be about MAS2 Former, which is a unified architecture for universal image segmentation. It was presented at this year's CVPR. The key idea in this work is basically that we want to train encoder-decoder models for segmentation, and we have three key improvements. The first is that we're going to use masked attention in the decoder, which leads to much, much faster convergence. The second is that we use improved multi-scale features. So if you typically use multi-scale features, they work well, but they come at a sort of increased computational cost. We show a trick in this work to use multi-scale features with encoder-decoder architectures, which makes them work at reduced computational cost, and we end up getting precise segmentation masks as well. The third key improvement is an improved loss function, which leads to much less memory usage, which makes this entire training pipeline super efficient to train on the GPU. All right. So the key result from this work is that we end up getting a model that is state-of-the-art on a bunch of different image segmentation tasks. So if you look at panoptic segmentation, if you look at instance segmentation, and if you look at semantic segmentation, while prior to our work, there were specialized architectures which were state-of-the-art on each of these three different benchmarks. So for example, for panoptic segmentation, the state-of-the-art was Max Deep Lab. For instance, it was SvenHTC, and BIT was the state-of-the-art for semantic segmentation. A prior work by the same author, Bowen Cheng, called MASFormer, presented at NeurIPS, actually was already able to do pretty well on all of these three tasks, but it had quite a bit of room to improve compared to state-of-the-art. And in this work, MAS2 Former, which builds upon MASFormer and has like these three key improvements that I talked about, significantly improves state-of-the-art on all three with the same exact architecture. The other thing we found is that we could just take MAS2 Former and apply it on video segmentation as well. It actually works pretty well. So on this YouTube 2019 VIS challenge, and also the YouTube 2021 version of the VIS challenge, MAS2 Former sets a new state-of-the-art for video segmentation. All right, so this brings me to the end of my talk. If you have any questions, happy to take them. I talked about these 3 works. The code for all 3 of them is online.
Yeah, thank you, Jen. Thank you for a great talk. Here comes the Q&A session. I wonder if there's any questions from the audience. Okay, so if there's no audience, question from audience, I do have 2 questions for Ishan. So the first question, you're talking about Omnivore. So for that work, and you're talking about actually 3 to 4 different modalities. Like you have the single image, you have the depth, you have the video, and also the 3D single view. So I wonder, because you mentioned that you want to do the 0 shot, you train on one single modality, and then it can be inferenced on the second modality. But as far as from my understanding that, because seeing from the classic computer vision, because usually if you want to infer, for example, like single image towards a single view 3D, you always select the depths or always select the camera intrinsic, and also you want to infer from the videos to the 3D, you also probably like a multi-view stereo, those kind of concept. So could you please tell us more about those insights or the details about why do you think it can work? Thank you.
Yeah, it's a great question. I think this actually brings, it's actually a question that is very sort of nice, detailed about the 3D part of it. So when we do single view 3D for Omnivore, we're technically not doing exact 3D. So we're not using depth, we're actually using disparity. So what ends up happening is basically now because to compute disparity, you've actually taken into account the camera intrinsics because you're looking at the focal length. And so all you're doing is basically just looking at relative depth. And so this was actually pretty important for us to do to actually make it work across different data sets. So the reason basically being that when we train on sun, which is primarily collected using, say, the access sensor and the kinetic sensor, you get a different kind of depth. Whereas if you test on something like O3D, which is a different data set where the depth is actually built by SFM, then the depth map is actually very different. So it's going to be in different units. It's actually like different types of depths also. So converting everything to disparity makes it much easier to actually test across different data sets. And this actually is inspired by the Midas work from Larkin and Colton's group, where they tried to predict everything in disparity. And that's how they are able to predict depth or disparity across Kitty and across a bunch of different natural image data sets.
Yeah, sounds great. That makes a lot of sense to me. Thank you. Yeah, so before I continue with the second question, let's see if there's any question that audience want to ask. Okay, so let me continue with the second question. So it's not actually a question, but I've seen a lot of impressive results you show for the Detic. So because we have the morning session, like Chunyuan has introduced the challenge about the computer vision in the wild, and also there is a sub challenge called object detection in the wild. I wonder if you're trying to think that whether the Detic that method can be applied on some existing detectors and can submit the results for that leaderboard. We really appreciate that this method can be also tried on we have 335 object detection data sets. So if you can also willingly to participate in this challenge, we will be really appreciated.
Yeah, thank you. Yeah, I will. So I'd actually spoken to Shingi about this, and it was just a little bit too close to the CVPR deadline for us to push right now, but we'll get around to it.
I see. Yeah, thanks. So we are also continuing to hold it towards maybe another CVPR workshop. So if you and Shingi have time there, you can please come and join us.
Yeah, thank you. I will.
Yeah, thank you.